Good morning, good afternoon, good evening, everyone. This is Mr. Eros Senna, and today we're going to talk about Newton's second law of motion. The other day we talked about Newton's first law of motion, so let's quickly review what that is. Um, Newton's first law of motion stated that objects stay in motion or they stay at rest until unbalanced forces act on it. And we kind of summed this up as the law of inertia, because we described inertia as the ability of an object to resist the change in motion. So if it has lots of inertia, it's really hard to get moving. And if it has lots of inertia, it's really hard to change its motion. And then on the flip side, if the object has low inertia, it's easy to get moving and it's easy to change direction. Okay? Now, Newton's second law of motion kind of builds on this a little bit, because it says that Newton stated his second law as follows: that an object's acceleration depends directly on the unbalanced force and depends inversely on the mass. Now, unbalanced force is usually described as a net force. So it's kind of like a net change in something. And we sort of touched on this a little bit in one of the assignment questions from the other day. Now, mathematically, Newton's second law can be expressed as follows. Acceleration is equivalent to whatever the net force is, and force is a vector, divided by the mass. So here it shows that the acceleration, A, is directly related to the net force. So if net force gets bigger, A gets bigger. And it depends inversely on the mass, which means that the smaller the mass, the more it'll accelerate. The heavier the mass, the slower it'll accelerate, which kind of goes along with our inertial law from the other day. If an object has large amounts of mass, you need large amounts of force to get it going. If it has small amounts of mass, you don't need as much force to get it going. Okay, so let's take a look at that, the first example. All right. So his first example asks us, what is the acceleration of a 2.3 kilogram object if a net force of 25 newtons is pulling on it? So let's draw a diagram. Lost my... All right, sorry about that. So let's draw a diagram. So we have an object. Okay, it's already telling us what the net force is. It tells us that the net force is going in this direction. Okay, so this is already the unbalanced force. Actually, it doesn't tell us what direction it's going. I'm just going to assume it's going in this direction. In your notes, you can make it go in whatever direction you want. Okay, mass of this object is 2.3 kilograms. Okay, so according to our formula, our acceleration should be equivalent to the acceleration should be equivalent, or is equivalent, not should be, is equivalent to whatever my net force is divided by the mass. I'm getting a little bit ahead of myself. By the mass. Now we're going to replace the net force with its value of 25 newtons and the mass with its value of 2.3 kilograms. Alright, so this will give us an end result of, pull up the calculator, there we go. So 25 divided by 2.3 gives us a mass of, this is obviously not in the correct Newton figures, mass of about 10.87, but with proper significant figures, this will be, what, 11. So 11 kilograms in proper significant figures. Oh, sorry, not kilograms, what am I talking about? 11 newtons per kilogram. My units will be newtons per kilogram. Newtons per kilogram. Okay. At the moment, this unit kind of doesn't make sense, because in our kinematics unit, we gave acceleration units of meters per second, or some velocity unit per time. This newtons per kilogram doesn't really make much sense like this. That's partly because Newton's second law has not always been written in this form. This is not the familiar form of Newton's second law. Newton's second law is actually written this way in most textbooks. So F net is equal to mass times acceleration. This is usually how it's written. And in this form, we find that the units for force end up being kilogram meters per second squared, which we conveniently we call this the Newton. This is the Newton force. So if I put the equivalent unit for newtons back into here, I get the following. 11 newtons is actually written as kilogram meters per second squared divided by kilograms. My kilograms will drop out, so I'm left with 11 meters per second squared, which is our unit of acceleration. There you go. All right. Now, if you have any questions, feel free to ask when I get back. Okay. Now, how do I find the net force acting on an object? Well, in order to do that, we need to draw what's known as a free body diagram. In the free body diagram, I've shown this to you before in class, but I never actually explicitly called it a free body diagram. What this does is it basically just shows you all the forces acting on an object. And then based on the forces acting on an object, you can tell where the unbalancing force or where the net force is going to end up. So let's take our example of our tables that you're sitting at. So the table you're sitting at is very similar to what I talked about the other day. Here's your table. And this table, there are two forces acting on your table. The first is gravity. So I'll put down gravity. That's the very first force acting on it. But I always mention, okay, if I have gravity pulling down, what is preventing the table from falling through the floor? Well, the floor is exerting a force to counteract that gravity. That's my normal force. And we know that the normal force is equivalent to the force of gravity. So in this way, there is no unbalancing forces. So no unbalancing forces. Which makes perfect sense. No unbalancing forces. Because it's not moving. The table is not spontaneously floating, and the table is not being dragged into the ground. So there's no unbalancing forces. So this object is, for all intents and purposes, stationary. There's no acceleration. Okay. Now let's suppose I start adding a force to it. Like let's say I want to pull. Let's erase this for a moment. Now I'm going to change things. So let's say I now add a force. Let's say I want to move the table and I start applying a force in this direction. We'll call this force pushing. Okay, now where is my unbalanced force? Well, I already know that the force of gravity and the normal force counteract each other, so I can effectively ignore these forces. Because those forces don't do anything because they balance each other out, they cancel each other out. So the only unbalancing force I have now is this force here, the pushing force. Okay. So if the unbalancing force is going in this case is going to the right, this means that my object will start to accelerate towards the right. Okay. And again, we saw this in the lab the other day with the toy cars. The toy cars, if they were applying an unbalancing force to the wooden block, and that's why the wooden block would move. Okay. So that's how you can sort of identify where the unbalancing force is. Okay. Now let's suppose I throw an object. So let's erase it. Let's suppose I throw an object through the air. So here's my object. I'm throwing it through the air. Now, once the object leaves my hand, so let's say I draw a person here. There we go. Once I throw the object, what is the unbalancing force on this object? I know it's moving in this direction. Okay, so this is my motion, direction of motion. Not the force, that's just my direction of motion. So once this object leaves my hand, what is the forces acting on it? Well, there's only one force acting on it once it leaves my hand. Let's draw that in red. That's gravity. Okay. Some of you might think maybe there's air resistance in there, but to be honest, we ignore that for the most part. But you wouldn't be incorrect if you said air resistance. Air resistance would actually cause it to go. I'll just draw that in just to show you guys. Let's do that in blue. So the air resistance is going this way. We'll call that FR. Okay. So this object, these are the forces that this object feels once it leaves my hand. Now gravity is going to cause the object to go down, and air resistance will cause the object to slow down in this direction. Okay. So here you actually end up having two unbalancing forces. So we have to figure out what the actual net force is between the air resistance and the force of gravity, and then we can figure out just what direction the force is going in, okay? Or what direction the unbalancing force is going in. But this kind of two-dimensional analysis is going to be saved for later, not quite right now. All right, let's go through an example. Okay, so we're just going to draw the free body diagram on a 35 kilogram box that is being pulled with a 55 Newton force to the right. And we're going to assume that this surface is frictionless. All right, here we go. So here's my box. Okay, so according to this free body diagram, we have one force pulling in this direction. We'll call that my pulling force. This is 55 newtons. And there's two other forces acting on this box. You guys have a moment to think about that. Then I'm going to write them in. Okay, so the first one is gravity pulling down. And the third one, or the second one, I guess, is going to be the normal force, which counteracts gravity. There we go. All right, so here are my forces. Now what is the unbalancing force? Well, just like in the previous example, the force of gravity and the normal force cancel each other out. So this is my unbalancing force. Unbalancing force. And it is causing it to move to the right at some speed or some acceleration. I'm not asked to find acceleration, so I'm not going to find that. That's the next example. All right, example 3. So here we have a sled that's accelerating at some acceleration. So I'm going to write that down, acceleration. And if there's a force of 20 newtons being applied to this sled. Now the sled is not, it's not on a frictionless surface, because it says right here that what is the force of friction? So there's obviously going to be a friction force acting, and it asks us what is the coefficient of friction. So let's draw a free body diagram. There's my sled. Physics, everything looks like a box. All right. So let us draw my applied force. So we'll just call this pulling. It could easily be a pushing force as well, but I'll call it a pushing force, 20 newtons. We know there's a force of friction in this direction, because the problem tells us there's a force of friction, and we need to calculate it. We have a force of gravity, and we have a normal force. And since we're going to assume the sled's not floating and the sled's not falling through the ground, so the normal force has to equal the force of gravity, which allows us to do the following. Allows us to cancel that out. All right. Now, how do I go about finding the unbalancing forces? Well, I can calculate that, because I know, based on Newton's second law, the equation for unbalancing force is as follows. Mass times acceleration. and I have the mass of the sled, which is 1.5 kilograms. I have the acceleration, which is 0.46 meters per second squared. So now I can calculate the net force this way. Let's do that. Calculate. Oops, I can't see what I'm doing. Alright, so 1.5 times 0.46. So this gives me an unbalanced force of 0.69 newtons. Okay, 0.69 newtons. Alright, now look at my diagram. How does this net force fit into this diagram? Give us a few moments to think about that. How does this net force fit into my diagram? Well, in my diagram, I've got two forces. I've got a pulling force going to the right, and I've got a friction force going to the left. Now, since they're acting in the kind of the same axis but different directions, it would make sense to do the following: that I can do that my unbalancing force or my net force can be the pulling force minus the force of friction. It's basically just like kind of trying to link it to something you might have seen before. Kind of like positive and negative numbers, I guess, on a number line. If you're going to the right, you're positive. If you're going to the left, you're negative, and then you just add the two numbers together. So in this case, that's exactly what I've done. I've taken my pulling force and I've subtracted my friction force from it, and that's going to be my net force. And I already know that my net force has to be 0.69 newtons, so I can just put in the numbers here. 20 minus force of friction equals 0.69 newtons here. So my force of friction, F, my force of friction is going to be, force friction will be, flipping things over, this will be 19.31 newtons. There you go. Now I know what my force of friction is. Alright, now, to calculate coefficient of friction, well, we can use the force of friction equation, which is mu times Fn. But I know Fn is equivalent to force of gravity, so I can just say mu times Fg, which we know Fg is just mu times mg. And then we just do that to solve for whatever mu is. We'll just pull this to a different screen. So I'm going to finish the calculation on this screen. Alright. Good. Alright, so my force of friction is going to be 19.31 newtons. I don't know what mu is. The mass of the block is sled is 1.5 kilograms. And G is 9.8 meters per second squared. Alright, so then mu, after some algebra, ends up being 19.31 newtons divided by 1.5 kilograms divided by 9.8 meters per second squared, which gives me, calculator, nope, 19.31 divided by 1.5 divided by 9.8. Ooh, it's terrible. I have a coefficient of friction of 1.313 something. In two significant figures, this would be 1.3. There we go. There's my coefficient of friction. Seems a little high. Must not be a very good sled, or the surface, or it could be pulling the sled on sandpaper. Yes, there we go. Alright. So a key thing, I guess, from this example is this part here. I'll highlight it in red. This. Net force can both be calculated as two forces or multiple forces adding together, or it can be calculated as mass times acceleration. Those are both valid ways, so both valid. Both valid. And it's really dependent on the context of the problem. All right. Yeah, I think I have one more example, and then you guys can get your assignment. All right, so here you have a 2 kilogram box pushed along a floor with a force of 25 newtons. This time we're given the coefficient of friction, and it asks us what is the acceleration of the block. So let's draw my block here. I'm pushing along with a force of 25 newtons. I've got a force of gravity here. I've got a normal force here, which is equivalent to gravity. And I've got a force of friction in this direction, which is currently unknown, but we can calculate that, I think. All right, so ultimately we want the acceleration of the block. How do I go about solving this? Well, first thing, I'm going to write down how force is related to acceleration, because that's really the only information I know. There we go. Okay, I know my mass, because that's up here. My mass is up here. There's my mass. Okay, I don't know my acceleration, and I don't know my net force. But thinking back to the previous example, can I calculate net force? Sure. So I've got a bunch of forces acting in similar directions. I know my my normal force is going to cancel out the force of gravity, so there's no unbalancing forces in that direction. But my force of friction and my pushing force, they won't fully cancel each other out. So I can say the following. So F net is going to be the same thing like the previous example, but this time I have a pushing force minus a force of friction. The pushing force is easy, that's just 25 newtons. I'm going to skip a couple of steps here and show that the force of friction is mu times mg. Okay, and refer back to the previous example if you're not quite sure. Okay, so I'll make a note here. See previous example, see example 3. Okay, this is how, because I'm skipping from, force of friction to straight to this formula. Okay, so this ends up being 25 newtons minus, we have our coefficient of friction of 0.5. We have a 2 kilogram block. And we have an acceleration of 9.8 meters per second squared. Okay, now we'll finish the calculation. Calculator. Oops, not the calculator. There we go. Load the calculator. So 25 minus 0.5 times 2 times 9.8. There you go. So our net force ends up being 15.2 newtons. Alright, but we're not done yet, because the question is asking us for what is the acceleration? Well, now we can go back and use this equation. We can use that equation. Alright, so F net, right over here, F net is mass times acceleration. We have a net force of 15.2 newtons. We have a mass of 2.0 kilograms and acceleration. So acceleration ends up being, hard to see, think about it. Let's see, 15.2 divided by 2, 7.6 meters per second squared. And there we go. There is my acceleration. All right. So once again, just like the previous example, you can calculate F net using sum of forces, or you can calculate F net using mass times acceleration. All right. Hopefully that all makes sense. You guys can put this into practice. And if you have any questions, come find me tomorrow or whenever I'm around.